You know, today we're going to talk about probably the most incredible piece of technology you will ever own, your own eye. We have this idea that it's basically a camera, right? Just snapping pictures and sending them to our brain. But the truth is, oh, it's so much cooler than that. Your eye isn't just capturing images, it's actually thinking long before your brain even gets the memo. So let me just ask you that straight up. Is your eye just a camera? Do you think it just passively records whatever is in front of it and sends like a raw video feed to your brain? And hey, it's an easy assumption to make. But what if I told you that's not even close to the real story?
That's the big idea right there. Your eye is not just a simple lens, it's this incredibly sophisticated supercomputer. It processes, it filters, and it even makes judgments about what's important before that information ever hits your conscious brain. It's an active partner in the whole process of seeing. So let's dive in and see how this all works.
Okay, so our journey begins the very instant a photon of light decides to enter your eye. Now, before any of the really fancy computing can kick in, the eye's optical system has a huge job to do. It has to take this chaotic flood of photons from the world and wrangle it into a clean, sharp image.
It's basically a tag team. First up, you've got the cornea. It does all the heavy lifting, providing most of the raw focusing power. Then, the lens jumps in. It's like the autofocus on a high-end camera, constantly fine-tuning the picture for stuff that's up close or far away. And while all that is happening, your pupil is making this really smart calculation. It shrinks down in bright light and opens wide in the dark. But it's not just about letting more or less light in. No, it's making a constant, delicate trade-off, balancing the brightness of the image with the sharpness to give you the absolute best picture possible in any situation. But here's the catch. The eye is a biological system, you know. It's not a perfectly machined piece of glass. And even with this incredible optical setup, there are tiny imperfections. These little flaws cause some of the light to scatter around inside the eye instead of focusing perfectly. And this creates a big problem called stray light. Think of stray light like a fine mist or a fog inside your eye. It casts this veiling glare all over the image that lands on your retina. And what that does is it kills the contrast, making it harder to tell the difference between light and dark. You know that blinding glare you get from oncoming headlights at night? Yep, that's stray light in action. So, in a perfect world, the cornea and lens would create this beautiful, high-contrast image, right? Just like this one. Sharp edges, crystal clear details, perfect. But this is the reality. This is that same image, but now with the effect of that stray light we talked about. See how that hazy glare just washes everything out? The details get muddy, the contrast drops. This is the actual messy image that the retina has to work with. And it's the very first problem our little supercomputer needs to solve. All right, let's move on to the next step, because this is where it gets really weird. Once that light, complete with all its fuzzy, straight-night imperfections, hits the retina at the back of the eye, it's time to turn it into an electrical signal the brain can actually read. And the way the eye does this, it's completely backwards from what you'd expect. I mean, just take a guess. If you were designing a light sensor from scratch, you'd probably build it so that when light hits it, it turns on and sends a signal, right? That's just logical. Stimulus equals response. Yeah, well, the eye completely flips that script. Most nerves in your body work that way. They power on when they get a signal. But your photoreceptors, the rods and cones that actually detect the light, they're different. When light hits them, they actually power off. It's because these cells are dark active. In total absolute darkness, they're on, constantly firing, constantly sending a signal. Light's job is to interrupt that signal, to turn them off. The absence of a signal is what tells the rest of the visual system, hey, there's light over here. It sounds totally bizarre, but it's way more energy efficient. You only have to signal a change from the normal state of darkness. And this is where the pure genius of the system kicks in. This single powering off signal immediately gets split into two totally separate channels. You've got the on pathway, which cleverly inverts the signal, so it reports when things get brighter. And then you have the off pathway, which just uses the original signal to report when things get dimmer. By doing this, the eye literally doubles its ability to detect changes in light, all from one set of sensors. It's incredibly efficient. So now we've got our electrical signal, and it's neatly split into these on and off pathways. So what's next? Does the retina just bundle all this information up and ship it off to the brain? Absolutely not. This is where the real onboard computing begins. I want you to think of your retina like a smartphone that comes with a bunch of pre-installed apps.
It knows it doesn't need to send the whole raw, high-definition picture to the brain. That would be a huge waste of energy. So instead, it runs these specialized apps to find and flag the most important features in whatever you're looking at first. So what kind of apps are we talking about? Well, there are circuits for edge detection. This is a core part of computer vision, and your eye does it instantly. It compares bright and dark areas to make outlines just pop, which, by the way, also helps fight that stray light problem we saw earlier. Then there are special cells for motion detection that only fire when something moves in one specific direction. And, get this, there are even hardwired threat detection circuits that are designed to instantly spot a looming object, like a ball flying at your face, and trigger a defensive reaction before you're even consciously aware of what's happening. Amazing.
Now, all of this amazing pre-processing, finding the edges, tracking motion, spotting threats, it all serves one final, absolutely critical purpose inside the eye: data compression. See, the eye has to take a massive amount of visual information and squeeze it down a very, very narrow pipeline to the brain.
Let's just start with this number: 125 million.
That is the number of photoreceptors, the rods and cones, that are initially capturing the light hitting your retina. It's like having a 125 megapixel camera inside your head, capturing this gigantic flood of data every single moment you have your eyes open.
But the optic nerve, that's the cable connecting your eye to your brain, it only has about 1 million nerve fibers. So, here's the puzzle. How on earth do you squeeze 125 million pixels of information through a cable that can only handle 1 million?
I mean, that's a compression ratio of more than 100 to 1. Think about that. The retina has to throw away 99% of the data it initially captures and somehow keep only the most important 1%. And it uses all those clever pre-processing apps to figure out what's important enough to keep. This whole brilliant strategy is called sparse coding. The retina doesn't bother sending a full, constant video stream to your brain. That would be insane. Instead, it only sends updates on what's new and important. Hey, an edge just appeared. An object is moving to the left. That shadow is getting bigger. The brain then just fills in the rest. It's incredibly smart. And that really brings us to the final mind-bending thought here. Your eye isn't just a window to the world. It's an intelligent filter, it's a data processor, it's a threat detector. It sharpens, enhances, and compresses reality before your brain even gets the message. So, if your eye is already doing all of this heavy lifting, all of this thinking, what does that really leave for your brain to do?